Let's go ahead now and we'll look at a few of the most common trig identities in the graphical calculator, and after we've done that we'll go and derive a few others by ourselves. So the first one here is cos squared plus sine squared is equal to 1. So there's two versions of this. So you can see here I've got the graph here of the sine squared, so that's sine squared, and this is the cos squared, and you can see here at each point when we add each of these up we're going to get a value of 1, and you can see that here whenever you put in sine squared plus cos squared we indeed get this value of 1. So we can also look at that in another way. So I can draw a circle here and I can put a point on the circle. So that's our point in the circle, and our point is going to rotate round about the circle, and we're going to have our y coordinate for the point, and we'll have the distance from the origin to the point, and we'll also have our x distance to the point as well. So you've seen these before. Now this is going to allow us to rotate the point round about the circle. So if I come up to the top here we have the value of x1, so that allows us to run the point round about the circle. Now we know that from our trigonometry that the sine of this angle here is given by the opposite over the hypotenuse. Now the hypotenuse is a value of 1, so it's just going to be the opposite over 1, which is just the opposite. So it means that the sine of this angle here is just this length. Well, this is this length here, so I've just put it up here, and the cosine of this angle is the adjacent divided by the hypotenuse. Now the hypotenuse again is 1, so it's just going to be the length of the adjacent, so this here is the length of the adjacent. So really this length here is the same as the value sine of theta, and this length here is the value cos of theta. Now from our Pythagoras we know that this length squared is going to be this length squared plus this length squared, but this length squared is just simply going to be cos squared theta, and this length here is going to be sine squared theta, and we're going to have our cos squared theta plus a sine squared theta. It gives us a value of 1, and that's what we see up here. We have our cos squared theta plus a sine squared theta equals 1, and you can see that the value remains at 1 all the way round the circle. So that's two little graphical proofs of cos squared plus sine squared is equal to 1. So let's move on and we'll look at some more. So here's our next identity here. Cos of x minus 90 is the same as sine of x. So there's a cos of x and there's the sine of x, and you can see that if we were to take the cos of x and we were to take away 90 degrees, well, whenever it's minus it's equivalent to taking the function and shifting it to the right. So we shift it to the right by 90 degrees, and when we shift this to the right by 90 degrees this cosine function will sit on top of the sine function. So we'll have our cos of x minus 90 will equal sine of x, and we can see this here because this is cos of x minus 90 here. So pi by 2 is actually 90 degrees. This is our radian measure, which we'll look at in a different video. But whenever I click on this, it'll just sit right on top of the sine x function. Now this is better seen when it's actually moving. So if we put in cos of x minus a, then we can actually shift the cos function about. So we set it here, this is the cos function just sitting on top of it where the value of a is equal to 0. But whenever we shift it along by a value of 90 degrees, it will sit right on top of the sine of x. So this tells us that cos of x minus 90 equals sine of x. So let's look at sine of x plus 90 equals cos of x. Again, we can put our sine x and cos x. So if we have sine of x plus 90, so plus 90 is plus pi by 2. So whenever I click this one on, this should just sit on top of the cosine function. And you see that here, it's just sat on top of the cosine function. Again, it's better seen whenever we actually move it. So if I put in sine of x plus b and I adjust it so the sine function sits on top of the sine function first of all. So that's when b is equal to 0. And whenever I move it, you can see it shifts to the left by 90 degrees and it becomes the cosine function. So we can see here then the sine of x plus 90 is equal to the cos of x. So it's just equivalent to taking the sine function, and plus 90 means shifting it to the left by 90 degrees and you get the cosine function. So now we'll look at the cos of x plus 90 is equal to minus the sine of x. So again we'll put in the sine and the cosine here. So it's the cos of x plus 90. So we take the cos of x, and plus 90 means shifting it to the left. So let's have a look and we'll see that actually shifting to the left. So this is this one here. So we're going to start it off at 0. So that's our cos of x. And whenever we add 90, we're going to shift it to the left. So let's go ahead and we add 90, and you can see it's shifting to the left until it gets shifted by exactly 90 degrees. Now what we've got is the cos of 90, cos of x plus 90 is equal to this function here. Well, this function here is nothing other than the minus the sine of x. Okay, so it's the sine of x flipped on the x-axis. So now let's look at the sine of x minus 90. This is equal to the cos of x. So again we can put our sine x and our cos x. So it's the sine of x we start off with. So we're starting off with this one here, and we're taking away 90. So by taking away 90, it means that we shift it to the right by 90 degrees. So let's go ahead and if we click on this here, and we'll start off with a value of 0. So at a value of 0, we're starting off with the sine x function, and we're going to shift it by 90 degrees, which means shifting it to the right by 90 degrees. So that's going to give us the minus the cos x. So this is the cos x up here. I'll get rid of this. So that's the cos x up here, and this becomes the minus cos x. Now another two important identities are the ones that deal with even functions and odd functions. So we say that the cos function is an even function. So what that means is if we were to pick the cos function up, notice that if I was to pick a value here, 0.5, and if I was to find the cosine of that value, it would be this height up here. But that would be the same as cos of minus 0.5. So it means that the cos of x is the same as cos of minus x. Now a function with that particular attribute is called an even function. And we can see here I've got cos x and we'll have cos of minus x. So cos of minus x should be exactly the same as cos of x. When I click on this, you see it just sits exactly on the top. So it's exactly the same function. So that is an even function. Now we're also interested in the sine function, and the sine function is an odd function. And we can see that if we were to look at, say, the sine of this value here, it's going to be this height up here. Now if we went along to minus 1, then the distance here would be exactly the same as the distance here, but it would just be negative. So what we're really saying is that the sine of x is the same as minus the sine of minus x. Now a function with this kind of attribute is called an odd function. So let's put minus sine of minus x on top of this, and it should just sit right on top. Like in fact, this is the same as this, and you can see it sits right on top of it. Now these are some of the most common trig identities, but we could keep going on and producing hundreds of trig identities if we really want to. But what we'll do is we'll go ahead and we'll look at another half dozen or so of the most common identities, but we'll just derive them mathematically rather than looking at them here in the graphical calculator. So here's the list of the trig identities that we just looked at in the graphical calculator. Now what we'll do is we'll go on the next page and we'll look at a few more trig identities, and then we'll go on and we'll look at a few examples. So we've got our final lot of trig identities here. Now we won't prove these here, we'll prove them, or at least some of them, within the exercises that we're going to do. So we can see that our sine 2 alpha is equal to 2 sine alpha cos alpha, and we have this lot here as well. Our cos 2 alpha equals cos squared alpha minus sine squared alpha, and that is equal to 2 cos squared alpha minus 1, which equals 1 minus 2 sine squared alpha. And these are our last two here, where cos squared alpha equals a half 1 plus cos 2 alpha, and sine squared alpha is a half 1 minus cos 2 alpha. Now we've already seen these two before, the compound angle formula, so I've just put these down as a reminder. Now you might be looking at these and thinking, well, what use or value are they? But they're actually quite useful whenever you're doing mathematics and you're able to swap round about different trig values. It does come in handy. But thing to note as well is that these aren't the only trig identities. You could go on creating as many trig identities as you want, hundreds, thousands, hundreds of thousands. You could just keep creating loads and loads of trig identities, but these are the ones that are kind of typical and that we tend to see used most often. So we're going to take all that we've learned before in this video and we're going to see where these trig identities are quite useful. So thank you for listening. I'll get you in the next video. Goodbye.